Okay, so now we're going to focus on a certain part of this graph here, which we're showing here, which is referred to as luxury consumption. So that's the in this next video clip, what we'll be focusing on in the first part of the clip here. So we'll start with the question of basically making sure we understand what luxury consumption is. What is luxury consumption? And we said that when nutrients are sort of in this range here, which was considered adequate, the nutrients actually limit growth in sort of a one-to-one, not necessarily one-to-one, but sort of a straight line, direct relationship where we have growth over here and nutrient supply here, or nutrient availability. And at some point it starts to level off, and that's where we refer to as luxury consumption. And basically what happens is the plant continues to take up the nutrient, but stores it instead of turning it into growth. So in the diagrams that we see below in the graphs, we're looking at time on the x-axis and days. In this graph, we're looking at the rate of phosphate uptake on the y-axis. And each of these different lines represents a different fertilization regime. So the green little dots here represent plants that were fertilized with 0.5 milligrams per liter of phosphate. And on up until, with an increase in levels of phosphate fertilization until we see 50 milligrams per liter being supplied here. So obviously plants that are supplied more phosphate overall have greater uptake, meaning that this blue line lies above all the other lines here. However, what we can see over time here is that, after a week of fertilization, we can see, there's a drastic difference between uptake rates of phosphate in the high fertilized plots or plants compared to the low fertilized plants, with sort of a gradient in between. But as time goes on, that high phosphorus supply doesn't necessarily translate into a continuous high uptake rate. So they do start to, decrease their rate of uptake over time here, as do plants that are fertilized with lower and lower levels of phosphorus until you get down to that, low level there. Now, if we compare, but overall, we can see that even after 60 days, the uptake rate of phosphate is still higher than all the rest, even though it's sort of down-regulated a bit. And when we compare this graph over to the right, where we see, again, the same legend and the same x-axis over days of fertilization, that the tissue phosphorus content, which is actually its concentration, is shown here with various plants with different fertilization treatments. So just to make sure we understand this value here, concentration is sort of the milligrams of phosphorus. This is tissue concentrations. Milligrams of phosphorus over the dry weight of tissue. And that's going to be, tissue is going to be in grams. So it's a ratio of phosphorus to total mass. And so if that mass stays the same, assuming luxury consumption is going on here in this part of the graph, this is luxury consumption of phosphorus, and the phosphorus content increases, then we're going to see an increase. Phosphorus content in terms of milligrams is going to increase. Then we're going to see an increase in concentration over this time period. And then, of course, it starts to level out here, where it's no longer taking up as much phosphorus relative to the amount of biomass, or perhaps the plant starts to grow at this point, or it just is actually what this part of the graph lines up with is over here, that the uptake rates start to just basically level out, which is going to flatten the concentrations over here. But in the beginning here, where uptake is higher and we see bigger differences between those treatments, we see an overall increase across all of these levels. And so, of course, luxury consumption is greatest, shown here at the top, than down here where the fertilization rate is lower. All right, so we can compare, sort of in contrast to luxury consumption, which is when nutrient availability is high. We can see what happens here on the left when nutrient availability is high versus low. So in this graph, we're looking at kind of a different way of looking at nutrients. Nitrogen, in this case, in litter fall, and this is content, sort of amount per area of the litter. And then that's being compared here to the biomass to nitrogen ratio of the litter fall. So what we're looking at then is when litter is high in nitrogen content per area of the litter, then it has a lower relative biomass. In other words, the biomass is more highly concentrated in the nitrogen, and so that might be reflecting what we see here as a luxury consumption. But what we're interested in is the term here called nutrient use efficiency, and nutrient use efficiency is defined as the amount of nutrients used per amount of biomass gained. And so you can see here what we're looking at is the biomass, which is in grams or milligrams, it depends on the plant, per nitrogen used or in the tissues. All right, so as the nitrogen content decreases, then we can see that ratio is starting to increase, where now we have higher biomass to nitrogen when there's lower nitrogen in the litter. So this area of the graph reflects high nutrient use efficiency. When low nitrogen is available, then it can still utilize what it has and increase its biomass content. It's not that this tissue has higher biomass than here, it's that this tissue has lower nitrogen content than here when we're looking at this part, when nitrogen availability is high. So when nitrogen availability is low, the tissue nitrogen is going to be low relative to the amount of biomass gained. When nitrogen availability is high, nitrogen content is going to be high relative to the biomass gain, which could be the same amount of biomass. It's just that it's the nitrogen level that's affecting that ratio. So plants can respond to limited nutrient availability by increasing their nutrient use efficiency. So if we put this into a question for this topic here, how do plants basically manage or survive with low nutrient availability? And it's just basically an adaptation, whether it's short-term or a lifelong adaptation. So if we turn that into this diagram here on the right, sort of apply that, in this whole scenario we're looking at kind of plant, soil, ecosystem dynamics, where we're looking at soils that are rich in phosphorus versus soils that are poor in phosphorus or low phosphorus availability. And so if we kind of start at this point here in the graph, basically when phosphorus availability is low, there's phosphorus poor soils, then the phosphorus content in the tissue is lower than when we have high phosphorus availability. Now, of course, if we back up one, here's that nutrient use efficiency graph, and we can see that nutrient use efficiency of phosphorus is higher in the phosphorus poor soils. So the tissue not only basically has lower phosphorus content, but doesn't necessarily mean when we compare it to the amount of biomass that the plant gains, it can do more with less. It has more biomass compared to the lower quantity of phosphorus, in contrast to high phosphorus content soils. Okay, so we'll start here and we'll continue following the arrows here. As this tissue becomes litter, then that litter is lower in phosphorus content, which is pretty straightforward when compared to phosphorus-rich soils. When that litter starts to decompose, because it has lower phosphorus content, it's the actual litter decomposes slower. And decomposition rate is measured as the loss of litter weight over time. So the actual litter itself is in phosphorus poor soils is decomposing slower, turning into humus at a slower rate. Not only is it because it's decomposing slower, then the regeneration of phosphorus in the soil is not only lower than in phosphorus-rich soils, but it's even below zero. So there can be sort of a immobilization of phosphorus, meaning not being made available to plants over a period of time. And so because of that, then we see that the nutrient phosphorus has a longer residence time, meaning that it stays in the soil longer. If it's decomposing and mineralizing slower, certainly it stays in the soil longer when that phosphorus content is low. And then again, this comes back around, low phosphorus availability means plants have lower tissue phosphorus and therefore have a higher nutrient use efficiency. So that's kind of how we would read this graph. One of the things that we want to highlight here, which kind of connects to the next figure, is the amount of the difference here between plant tissue phosphorus in phosphorus-rich soils versus phosphorus-poor soils. And this is about a 40% difference. And so when that tissue phosphorus, or when those tissues become litter, then we would, in general assume, without any prior knowledge, that there would be the same difference in content of the, down here, in the phosphorus content in the litter between phosphorus-rich soil and phosphorus-poor soil. But what we see, in fact, is that there is about a 60% drop in the phosphorus content in the litter compared to in phosphorus poor soils compared to phosphorus content in the litter coming from phosphorus rich soils. So the question is, what happens to this 20%? Where did it go? Well, that links us to the next figure here, where we see a term which is called resorption. And so this is referred to as resorption. And resorption is defined as the remobilization of nutrients prior to tissue loss to litter. Or we could refer to that, for example, as leaf abscission. And that's basically where leaves drop off in deciduous plants. Okay, so the question we could ask here basically is, how do plants conserve nutrients trying to write fast here, when they lose biomass, when they lose biomass naturally. We're not talking about from herbivory or logging and so forth. But we're looking here at nitrogen and phosphorus. Now both of these are mobile nutrients within the plant, which has some effect on this. But what you see basically across all these different kinds of plants is that somewhere between 40 and 50% of the pool of nitrogen within the plant gets remobilized or resorbed. Resorption is the term here, before abscission. And the same is true with phosphorus, which is also mobile in the plant. Somewhere between 40 and up to 70% in grasses that gets remobilized to the live tissue before they lose the tissue to litter. And so this is basically nutrients in older tissues are reallocated to younger tissues before they lose the nutrients to litter, and that helps them conserve nutrients.